research has been focused on using Cassini data, which is a spacecraft that's currently in orbit around Saturn. And we are trying to constrain the particle size distribution of the rings. So the rings are made up of all these different particles, from the size of micron-sized dust up to boulders the size of houses. And these all orbit around Saturn in what we see as the rings. And understanding the particle size distribution actually gives us information about what's going on in the rings. So if there's a lot of small stuff, that means these things are probably colliding pretty frequently and throwing off some of the smaller material. Otherwise, that would get swept up or accreted back onto the bigger rocks, ice rocks that are orbiting Saturn. So understanding the particle sizes actually teaches us a lot about the dynamics, the ongoing dynamics of the rings. The way that we do this in my research is actually by looking at diffraction, and this is what we're seeing in this picture. It's forward scattered light. And so the concept of this, as my advisor likes to use of the example, is when you see, if you're in a movie theater and you look back up towards the projector and you can suddenly see all this dust floating around, that's the same principle of what we're using here. So that's because those dust grains actually are more effective at scattering light in a direction into your eye when they're in that projector light, not when you're looking directly at that dust material. It's not necessarily very reflective. So we use that to actually measure the particle size distribution in the rings, because the smallest stuff is going to scatter light with a certain intensity. And so you can use that intensity to determine, to backtrack out what those particle sizes must be. So we do this in what we call stellar and solar occultations of Saturn's rings to constrain the particle sizes. And we found things like we've set a pretty strong minimum particle size that exists in the A ring, which is this big outer ring here. And we're doing a lot of work with the F ring, which we know is a very exciting ring that has lots of cool collisions and ongoing dynamics and moonlets kind of crashing through the ring. So we do this all computationally to basically reproduce through computational models. We reproduce the data that we observe with these diffraction signatures in them.